Hey folks, I hope you're doing well. This is a short video about exponential functions, which is section 4.1 in your book. So we're skipping a lot of chapter 3, which gets a little more heavily algebraic than we need to. Also, we're just going to do this one section in this video, and then in the next video, we'll do section 4.3, and those will be the two sections on the quiz on Friday, July 30th. If you're taking the summer 2021 class. All right, so let's start with some review, and I expect that the stuff here you have seen before, but exponential functions are closely related to percent change, so it's worth reviewing some basics of that first. So first of all, how do you compute the percentage of a number? Say you want to take 6% of 9,000. Well, you all know that 6% is 0.06. And so the way you get 6% of something is you just multiply the number by 0.06. So 540 is 6% of 9,000. Okay, fair enough. How do you increase something by a percentage? Say you have an asset worth $500 and it increases in value by 14%. How do you find its new value? Well, notice we don't just want to take 14% of 500. That would be a much smaller number than 500. The new value should be more than 500 since it's increased in value. What we do is we take the 500 and we add 14% of 500, right? So we take 500 plus 500 times 0.14. And instead of just computing this, and of course you could just put that in a calculator and figure out that the answer is 570, I'm going to do a little algebra here and factor out the 500. So that happens here, right? I pull the 500 out and I'm left with 1 plus 0.14. And the 1 plus 0.14 is 1.14. And so I get this expression here. And this is useful because it gives me kind of a shortcut way to increase or decrease something by a percentage. If I want to increase something by 14%, I just multiply it by 1.14. So here are a couple of examples of that phenomenon. Oops. If I want to increase, say, 1,280 by 27%, what do? I just multiply by 1.27. And this is my result, right? So now I can change something by a percentage by just a single multiplication. That's kind of the important observation here. If I want to increase 88 by 3%, I just multiply it by 1.03, and there's the result. Another example, if I want to decrease a number, so this is a little different. What happens if 950 goes down by 20%? Well, if you go back up to this expression here and think about what would happen is instead of adding the change here, you'd be subtracting it. So this plus would be a minus sign. And what I want to do to get this factor is subtract the percent change from 1. So 1 minus 20% is 0.2 is 0.8. And so I just multiply 950 times 0.8. So I can kind of move something by a percentage, whether up or down, just by a single multiplication. Again, this is just a review of some basic arithmetic, but it comes up a lot when dealing with exponential functions. Okay, one final example. What if we know the beginning value and the end value, but we want to know what was the percent change, right? So if 100 increases to 107, well, in this case, because the numbers are, the first number is 100, you should be able to eyeball the fact that that's a 7% change. But in general, what we do is we take the difference between the two, new minus old, and divide by the old, right? So that's 107 minus 100 divided by 100. And that's where, if you do a little math there, you come out with 0.07. Which of course is 7%, right? Again, worth emphasizing that 7% and 0.07 are the same thing. Okay, so let's take an example here, to introduce exponential functions and compare them a little bit to linear functions. So suppose I have two assets, call them asset A and asset B, and they're both worth $100, and they're both growing in value over time, but they're growing differently, right? The first asset grows by $10 each year. So this is a little bit of simpler growth than the second asset, which grows by 10% each year, right? So the first asset is worth $100 now. In a year, it's going to be worth $110. In 2 years, it's going to be worth $120, then $130, $140, and so forth. It just adds $10 every year. And if I let t B, measure the number of years, and let A of t be the value of the asset in t years, right? So in our function here, the input t is the number of years that go by, and the output is the value of asset A. And here's the simple formula, right? I just take 100 and add 10 times the number of years that go by. So after 9 years, it's grown by $90, right? 9 times 10. And so 100 plus 10 times 9 gives me 190 for the value of asset A. All right, what about asset B, which has a little bit more complicated growth scheme, growing by 10% per year? Well, the idea of our model will be the same. Again, we'll have an input variable t that measures years, and we'll have a function which we'll call b of t that measures the value of asset B. It's not as obvious, though, what the formula should be for b of t. So when you're in this situation and trying to sort of build a model and you don't even know what form the function takes, compute a few sort of easy values. So start with b of 1, right? So b of 1 is the value of asset B after 1 year. Well, after 1 year, it grows by 10%, and we know how to grow something by 10%. You just multiply it by 1.1. And so there's the value for b of 1. All right, well, what about b of 2? Well, for b of 2, what I'm going to do is take the amount after 1 year and grow that by 10% because it grows 10% every year. So here is the value after 1 year, and I multiply that by 1.1 to increase it by 10%. And notice that that's just 100 times 1.1 squared. Okay, what about b of 3, the value after 3 years? Same idea. I want to take what I have after 2 years, which would be this right here, and grow it by 10%, which means I multiply it by 1.1. And when you multiply by another 1.1, that 1.1 squared becomes 1.1 cubed. And if you do that on a calculator, you get 133.1. Well, I can kind of see the pattern here, right? Here's b of 1, here's b of 2, here's b of 3. So what's changing from value to value is the exponent here, right? b of 4 is going to be 100 times 1.1 to the fourth. And in general, b of t is 100 times 1.1 to the t. This is an example of an exponential function because the input variable is in the exponent. That's where the name comes from. And we'll get a little more precise about their form in just a moment. For now, let's take a quick look at some values of these assets. So here's the asset A column, and this is no mystery, right? Just grows by $10 every single year. Asset B, again, a little bit more complicated. We computed the first 3 of these up above. And then if you go ahead and plug in t equals 4, t equals 5 on your calculator, you find those other 2 values here. So it looks like that you would rather have 10% each yearly growth than $10 yearly growth, right? Asset B is doing better than asset A. Here are the graphs of the 2 functions. Right, so asset A is and notice, by the way, I should have mentioned this here, asset A is a linear function, right? We talked about linear functions before. Slope or average rate of change is 10, y-intercept is 100. So asset A, of course, graphs as a straight line. That's a linear function. And here's the value of asset B, and I've allowed us to vary the fixed dollar growth rate. So here asset A is growing by $40 a year and asset B by 15% a year. So let's change these so that they match our values above. And here you can see asset B is doing better because the orange curve is always higher than the blue curve. If you turn up the growth rate for A, so now asset A grows by $20 a year instead of $10 a year. It's not as clear. Now A is doing better most of the time, but eventually B catches up, right? So this is out at about 14 years. So that's a long time, but if you're willing to wait that long, asset B will start to do better. And of course, if you turn up the percentage growth rate, you can see that asset B starts to do better. The orange curve goes up, so now it's growing by 16% per year. Okay, so we've got 2 sort of models here. We have a linear growth model for A, and this is an exponential growth model for B, and we'll talk more about exponential growth model exponential growth models now. So the general form of an exponential function is this. We will have another form coming soon, but this is the sort of basic form, a times b to the t. So in our example up here, here's a, 100, and here's b, 1.1, right? So b, the letter b is for base. It's the base of the exponential, and a is just constant outside of the exponential. So it's very common with exponential models for the input variable t to measure time. Exponential models are often used to measure the change in something over time, and usually the output measures some quantity. So it's the amount of something. It could be the amount of financial value, as in the examples we were just talking about. It could be the size of a population. It could be the amount of a chemical that is decaying radioactively. There are a number of different things it could be, but a common model for exponential functions is to measure the change in the size of a quantity over time. If you plug in t equals 0, so this is how we get the y-intercept for any function. We just evaluate the function at 0. So you get a times b to the 0. Anything to the 0 power is 1. So this is just a. And the virtue of this calculation is it gives us an interpretation for this number a. Now it has a meaning. It's the y-intercept of the function. It's also the time 0 value of the output, right? T equals 0 is kind of the starting time for a lot of our models. So we'll often think of A as the initial quantity or the time 0 quantity for whatever it is that we are talking about. B comes from the growth rate, right? Up in our example, B was 1.1, and that came from the fact that the asset was growing by 10% each year. Notice that if you take, say, f of 6, so that's a times b to the 6, again, the input is just in the exponent, and do a little bit of algebra here, right? B to the 6th is b to the 5th times b, and this first thing is just f of 5. So f of 6 is b times f of 5. And f of 9, same kind of calculation, is b times f of 8, and f of 12 is b times f of 11, and so forth. That is, the quantity size at any time is always b times the quantity size in the previous time period. So b measures the sort of time unit to time unit, year to year. So here I'm saying 1 year in the future. Time can be measured in months or days or weeks or seconds or whatever. So it might be better here to say the amount 1 time unit in the future is always b times the amount now. All right, so let's look at an example. So here's an exponential function, right? It has the form ab to the t. A is 450, it's the number out front. B is 1.23, right? So right off the bat, I can see that if this is modeling a changing quantity, the initial amount of the quantity is 450, and the quantity grows by 23% per time unit, right? I can read that right off the form of the function without doing any math. Up in our earlier example here, we had an initial amount of 100, and the 1.1 came from the fact that it was 10% growth per time period. Okay, so let's get back to, I may have already said everything that we're going to show here. Indeed, right? Initially, the quantity is at size 450, and it grows by 23% per time period, whatever the time periods are. And again, what that means is the amount 1 time unit, it might not be years, in the future is 1.23 per times the amount now, right? 23% growth per time period. This I worry might be code. Yep, that's code. Let's put that away. And just look at a graph of this function. Or actually some numerical data. So there's an input-output table for this function. I've got some t values and some function values. And you can see indeed that the quantity grows over time. And it grows pretty quickly. 23% is pretty rapid growth. You can see that by time 4, it's more than doubled, right? Started at 450, it's already up to 1,030 or so after 4 time periods. All right, look, here's an exercise from the notes and exercises. Suppose that you own an asset that's worth $100 and it increases in value by 5% every year. Let's see if we have this problem so that we can see what the questions are. 0.5 was, here we go. Right, so first let's come up with a formula for the value of the asset V as a function of the number of years that go by T. So this is a similar example to the one that we did before. And now hopefully you can just write down the model, right? The initial value is 100. If it grows by 5% per year, then the base of the exponential is 1.05. So here is our model, 100 times 1.05 T. Okay, how much is it worth in 1 year, 2 year, 3 years? Well, these questions now are all pretty straightforward. I have a formula for what it's worth in T years. So to get the amount in 1, 2, or 3 years, I just plug in T equals 1, T equals 2, T equals 3. And here are the results, right? Again, I expect you all have a calculator. If you don't, where did Google Calculator go? There we go. Here is a calculator, right? So I could do 100 times 1.05. And the way that you do exponents on Google Calculator is this X to the Y button down here. There we go. And you can see a little box shows up. And let's say I wanted to see the amount in 3 years. 115.7625. And that's the amount that we got right there. Okay, and the final question in this exercise, how much is it worth in 18 years? Again, just more plugging into the function. I'm just going to calculate V of 18. Right, and I get 240.66. And again, on Google Calculator, so let's clear that, 100 times 1.05 raised to the, there we go, 18, and click the blue equals, and that's the same value that we showed in the notebook here. Okay, so let's summarize some of what we have learned so far. There's the general form for an exponential function, AB to the T. We know what A and B means, right? A is the initial or time zero quantity. B is called the growth factor. So that's the name that we'll give to it. And it comes from the rate of growth, right? If the rate of growth is 5% per time period, it's 1.05. If it's 23% per time period, it's 1.23, and so forth. So notice that the relationship between B and the growth rate is you subtract 1 from B to get the growth rate, right? If B is 1.05, the growth rate is 5%, right? 1.05 minus 1. If B is 1.23, the growth rate is 0.23 or 23%. And so here's just an example, right? If the base were 1.12, then the growth rate's 12%. Notice that the base could be less than 1, right? If the base is 0.93, then the growth rate's going to be negative, right? 0.93 minus 1 is negative 0.07. So when the base is negative, we have a quantity that is declining in value or declining in size rather than increasing in size. So we can have exponential models that model things that grow and also things that decay or decline, right? And what determines that is whether B is bigger or less than 1, right? Bigger than 1 is exponential growth. Less than 1 is exponential decay. This phrase, growing exponentially, you've probably heard, and in sort of common speak, people usually interpret that to mean kind of wicked fast growth. That's sometimes true, but not exactly. And we have a much more precise understanding of it. Something is growing exponentially if it's modeled by a function that looks like that, AB to the T. All right, so here are some graphs. So here I have an exponential model where the initial quantity is 500 and it grows by 17% per time unit, right? So the growth factor is 1.17. So if I turn down the growth factor, you can see that the curve moves down. It doesn't grow as quickly, right, as I decrease the growth factor. And conversely, as I increase the growth factor, the growth gets more rapid. Likewise, if I start with less, so here A is the initial value, notice you can see A as the y-intercept over here on the left. So if A declines, again, the whole curve kind of sags, because if you start with less, then you're going to wind up with less, even if it's growing. And conversely, as we move A up, right, the curve rises, because if you start with more, you're going to finish with more when you're growing exponentially. This is what it looks like if the growth rate is less than 1. So you can see the values over here on the right. The growth factor here is 0.9. So this is a quantity that is declining by 10% per time unit. And you can see the initial value over here is 80, the y-intercept, and the curve goes down because the quantity is decreasing. Now, if I move this up, that's going to be a smaller rate of decrease, right? If I move this up, let's say to 0.95, now it's only declining by 5% per time period instead of 10%. And so the curve doesn't go down as sharply. On the other hand, if I shrink B, the decay becomes more rapid, right? Now I have something that's declining by, let's say 0.82. So that's declining by 18% per time period. And the initial value, again, is the y-intercept over here. If I move this up, the curve comes up. If I move this down, the curve goes down, right? If you start with more, whether you're growing or shrinking, you'll end up with more. And if you start with less, you'll end up with less. All right, here's an example. Suppose I have a city and I have some population information. It's currently, there's 10,500 people in the city. It grows by 4% each year. And we're going to build an exponential model that gives the population of the city T years from now. Okay, so I know right away that because of this phrase exponential model, this is what the function looks like, right? That's what an exponential model looks like, a times b to the t. I also know the a value because I know the initial quantity is 10,500, so I can fill that one in. And I also know, because it grows by 4% each year, that the b value should be 1.04. So in this situation, we can pencil in the parameters right away and get to our model. So I think this now will ask a question about this. What do we estimate the population will be in 2036? Well, it's 20. So notice here, T measures years from now. It's 2021 now. So 2036 corresponds to T equals 15. Let's see if we did this right. Nope, this should we want T equals 15. So let's make that a 15. Make that a 15 and go to Google Calculator to see what that should come out to be. So let's clear things. 10,500 times, and what was it? 1.04 was the growth factor. Raise that to the 15 power, and I get 18,909.9. So that's what this should be. I'll round up. All right, so there is our answer. So we can build a model. Once we have a model, we can estimate the size of the quantity at any time, after any number of time units, just by plugging in. Okay, a little more comparisons between linear and exponential models. So here's an input-output table. The question is, could this represent a linear model? Well, how are you supposed to know without knowing the formula of the function? The key here is to remember that linear functions have a constant average rate of change. And we can check this in the table, right? The average rate of change here is not constant. As the input goes from 0 to 1, notice here the output goes up by 15 from 20 to 35. But here from 1 to 2, the output goes up by 25 from 35 to 60. And here, as the input goes from 2 to 3, the output goes up by 4, right? And so the input increase is the same in every case, but the output is not changing at a constant rate. So this is not a linear model. We don't know what kind of model it is just based on this information. Okay, could this table represent an exponential model? Now, doing the same kind of analysis we just did, you can quickly see it's not a linear model. How do we assess whether it's an exponential model? Exponential models have a constant percent growth over from one time period to the next. And we can check this as well, right? The output should increase by the same percentage. So that means whatever percent increase that is, this should be the same percent increase. And this should be the same percent increase if it's going to be an exponential model. Well, we can check that, right? We just do new minus old over old. So here is the first calculation over that first interval, and do that on a calculator, you get 0.09. Here's the calculation over the second interval. Again, loaded into your calculator, you get 0.09. Here's the third interval. I get 0.09 in every single case. So just based on this table, this could be an exponential model because I do have a constant percentage increase, right? For every time the input increases by 1 unit, the output increases by 9%. So it's plausible that this could be from an exponential model. Obviously, we only have 4 data points, but just based on what we can see. And the key things to sort of take away here, again, is we're comparing 2 of our model families, linear and exponential. Linear functions have a constant average rate of change. Exponential functions have a constant percentage rate of change. Okay, so again, there are some exercises done here. I'll open these up in the notes, but I won't talk about them right now. Let's move on with some other examples of building exponential models. So suppose, again, I have a population of a city that's growing exponentially, but this time I'm not given the growth rate. I'm just given a couple of data points, right? I know it has 64,000 residents in 2000 and 68,500 in 2004. So I want to find an exponential model, so I know that that's what the model looks like, that gives the city's population T years after 2000. So when you're building exponential models, it's important to be very specific about how you measure time. Don't say something like T equals time. What time, right? The time you have lunch, time from noon today, time from last week. Something like T years after 2000 is a much more precise way to specify the value of the input. Okay, so T equals 0 here, notice that's the T equals 0 is the initial time, and that's the year 2000, right? Because we're measuring T years after 2000, so T equals 0 is the year 2000. And we know the population there is 64,000. So we have a leg up on our model, right? F of 0 is 64. Notice that we're measuring population in thousands. And so the model starts to get specified a little bit. I can fill in the A value. I still don't know the B value. But I do have more information I haven't used yet, right? I know that F of 4 is 68.5, right? 2004 corresponds to T equals 4. And that gives me this equation, right? On the right-hand side here, I've plugged T equals 4 into my model, and on the left is the value that that's supposed to be. If I divide both sides by 64, so I just do a little bit of algebra there, I get b to the 4th is 1.07. So a word about solving equations like this, I want to solve for b, but b is raised to the 4th power. The way to do this is to take 4th roots on both sides, or what's an even better way to think about it, to raise both sides to the 1/4 power. So I raise the left to the 1/4 power, and I raise the right to the 1/4 power. The advantage of this is that when you raise a power to a power, like on the left, you multiply the exponents. 4 times 1/4 is 1. So I just get b, which is what I wanted. I wanted to solve for b. And then you get this thing, which looks kind of complicated on the right, but we can just do that on our calculator. So let's see. I'll clear this and do 1.07 raised to the, I think oh, there we go. Okay, raised to the, and now I just want to do 1/4. I'm going to use a parentheses to make sure that that thing is all in the exponent. And then I click equals, and there's the result, 1.017, which is what we got here. Okay, so now I have the b value, and I have what's sometimes called a fully specified model. Here's my model for this city's population, and now I can estimate the population in any year after 2000 just by plugging in the appropriate t value. All right, here's another example. Suppose I have a radioactive substance that decays exponentially as some as some do. So exponential models are commonly used to model radioactive decay. We begin with 110 milligrams of the substance, and we've got some information about how it decays after 31 hours. They take a measurement, and there's only 55 milligrams of the stuff left. All right, so let's first write down our model. And again, I'm going to be precise here about what this means. F of t is the amount of substance. Let's even include the units in milligrams left after t hours. So t hours after whenever the beginning is here. Okay, so I know the initial amount. Well, so first of all, I know what the model looks like, right? Anytime I have exponential change, the basic model is ab to the t. I know the initial amount is 110, so I can fill in the a value, right? So my model gets a little bit specified. And the other thing I know is this piece of information, right? That after 31 hours, there'll be 55 milligrams left. And that means that f of 31 is 55, right? When I plug in the time value 31, the result should be 55. So here's what it looks like when I plug in t equals 31, right? The t is up in the exponent. And again, I get an equation that I can solve for b. I'll divide both sides by 110 first. And note before I do that, that 55 is half of 110, right? So this 31 hours is sometimes called the half-life of the substance. It's the amount of time it takes for the thing to decay to half of its original size. So you will see that term half-life in some examples. So back to my equation, when I divide both sides by 110 here, I get 1/2 on the left, and on the right, it's just b to the 31. And we saw above how to deal with an equation like this. I just raise both sides to the reciprocal of that exponent, which is 1/31. And I get this thing that looks a little messy, but I just go to my calculator. So let's clear out again. So I want 1 divided by 2, that's 1/2. Raise that to the, what was it again? 1/31. 1 divided by 31. Close parentheses. And there we go. So 0.978, or sorry, 9779. Is that right? Yeah, 9779. Okay, so now we have fully specified the model, right? I knew A was 110. I just filled in the B value. So there's our F of t. What's the question again? How many milligrams will remain after 42 hours? So all I have to do is plug in a t equals 42. Right here, do this on my calculator, and I come out with about 43. It makes sense that there's less than 55 milligrams left, right? Because the thing is decaying, and 42 hours comes after 31 hours. All right, let's talk about compound interest and do 1 or 2 more examples. This is going to be a little bit longer screencast than usual, but that's okay. So compound interest is a model for the growth, not just of money, but of financial value, I would say, of any kind. So the basic scenario that's useful to keep in mind when thinking about compound interest is we invest a sum of money at a given nominal or annual interest rate. So it might not be an investment of money. It could be really any asset that's growing in value. And here are the sort of key parameters. Let's just introduce all of them at once. Right, I'm going to let A be the initial amount, the amount I invest. T be the number of years that goes by from the time of my investment. R is the interest rate. And K is the number of compoundings per year. Now, I'm not going to bother to take the time to derive this formula. Let's see what's down here. Oh, yeah, so a word about K, right? So these the first 3 are pretty straightforward. Number of compoundings per year, you'll often see this expressed as like monthly compounding or daily compounding or quarterly compounding. It's worth noting how to translate this into K values. If you compound monthly, that's 12 times per year because there's 12 months in a year. If you compound daily, we'll ignore leap year and take K to be 365 days in the year. Quarterly, there's 4 quarters, so K equals 4. Okay. And so if A of t is the value of the investment in t years, here's the formula for A of t. Again, I'm not going to take the time to sort of derive this formula now. And in a remote course, you don't have to memorize it. It's here in the notes. You can always grab it when you need it. So an example of compound interest. Suppose I invest $4,000 at 6% compounded monthly. How much is, I guess it's you, not me, is your investment worth in 5 years? Well, it's just a matter of identifying all the right values on the right-hand side here and plugging in. Right, A is 4,000, that's the initial investment. The rate is 6% or 0.06. T, the number of years it goes by, is 5. And since we're compounding monthly, K is 12. All right, so I just load that into that formula. That looks like this. Plug that into a calculator, and I come out with this value. Okay. What is the effective annual rate? So again, when you when you put money in the bank or in a CD or something like that, although these days interest rates are almost zero, but in general, you are quoted a sort of nominal rate, but then you get an effective rate. Because of compounding, the rate of return is actually a little bit different than the quoted rate. So how do we figure out what this effective rate of return is? Well, there's a formula for it, but the way I like to think of it is just invest $100 for 1 year at the scheme, use this formula to figure out how much it grows to, and you'll be able to see what the percent change is, right? So for example, here, so A is 100, and I'm using the same scheme as up above. T now is 1. I'm only letting 1 year go by. But the rate and the compoundings come from whatever the compounding scheme is. We're talking about 6% monthly, so R is 0.06 and K is 12. Load those into the formula. I come out with this. So my $100 grew to $106.17. And because I started with $100, I'm staring at the percent change, right? It changed by 6.17%. And so that is the effective annual rate, 6.17%. Okay, let's quickly talk about Euler's number and continuous growth, and that'll be good for exponential functions, which is again section 4.1 in the book. So what is Euler's number? Well, if we do the following thought experiment, invest $1 at 100% interest for 1 year, and we change the number of compoundings, right? Because what you'll notice if you do some of these calculations is compounding helps a little bit, right? If you just grew $100 by 6% for a year, you'd have $106. But if you compound the 6% monthly, you get a little more than $106. So a question is, if we kept turning up the compounding, could we make our $100 grow into like millions and millions of dollars? Well, so let's strip this down. $1 at 100% for 1 year. If there is no compounding, or should you just compound once, $1 grows by 100%, becomes $2. All right, well, I've done the calculations here for various number of compoundings. So this is almost monthly. Monthly would be 12, not 10 compoundings. And our $1 grows to about $2.59. Daily compounding is roughly here, right? It's 365, so it's close to 350. Now I'm getting $2.71 or so. What about 1,000 compoundings? So this is compounding like 3 times a day. Still only $2.71 or 72 cents or so. And you'll notice the numbers in the right-hand column. At first, it looks like, yeah, we're doing better as we compound more. If we compound millions and millions of times, maybe we'll be rich. But by the time you get down here, these numbers are barely changing as we up the number of compoundings. And it turns out that the numbers don't grow without bound. Instead, they kind of flatten out. And they flatten out at this number, which is called Euler's number, and will symbolize with an E. Now, I'll use that funny looking E. You can just use an ordinary letter E to symbolize Euler's number. Euler's number is important for a lot of reasons in mathematics. We will use it to give us another form of exponential models. So one form is A times B to the T. Another form is a times e to the RT. And when the model is in this form, R is called the continuous growth rate of the quantity. So I think a quick example here. If R is positive, we have a growing quantity. And if R is negative, we have a decaying quantity. All righty. Right, so here's a quick example. Here is an exponential model that is written in continuous growth form. A is still interpreted the same way. It's still the initial value, right? So this is still the initial quantity is 75, but now the continuous growth rate is 8%. So in the old form, what we could see was the per time unit growth rate. Now we can see the continuous growth rate. And here, so notice here, I have a negative sign in the exponent that cues me that this is a quantity that is decaying, not growing. 200 is still the initial value, and the continuous decay rate is 11%. All right, quick example, and we'll be done here. Suppose I have a population growing and I have the continuous growth rate, right? So I'm given the continuous rate of growth at 6.3%. Current population is 450,000. We want to model for the population T years from now. All right, well, since we're given continuous growth rate, it makes sense to use the continuous growth rate form. The A value is 450. Notice that I'm measuring population. Well, we should say this here. Let's measure the population in thousands. 2 years from now. So here's the initial value. I just plunk the continuous growth rate into the exponent there. How large does the population estimate? How does the model estimate the population will be in 10 years? I just have to plug in a 10. And you should have an E to the button on your calculator, on Google Calculator. You can see the E value right there. So let's clear this out. Do 450 times E raised to the, what do you want to raise to? 0.063 times 10. When you are working on a calculator and you have stuff in the exponent like this that has to be computed, put it in parentheses, right? So I'm going to use a parenthesis 0.063 times 10, close parenthesis like that. And so 844.92, and that's the result that we get here. Okay, so we predict the population. Notice this is in thousands, right? So we predict the population will be about 845,000 people. Okay, finally, it's worth noting that if you take a model that is in continuous growth rate form, it's not hard to rewrite it in our old form, right? All I have to do is use this property of exponents that when I raise a power to a power, I multiply exponents. And I can do e to the 0.063 on my calculator. So back here, e raised to the 0.063, 1.065, right? So that's where that number comes from. And now it's in good old AB to the T form. So notice a continuous growth rate of 6.3% is a per time unit growth rate of 6.5%, right? So not exactly the same thing. All right, that's an introduction to exponential functions. This is section 4.1 in the book, and the quiz Friday will be 4.1 and 4.3. Take care of yourselves, folks.